Hey everyone, welcome back to the channel Code with AKJ. Today is day 38 of solving LeetCode 75 challenge, and today's problem is lowest common ancestor of a binary tree. So it's a frequently asked question in interviews from companies like Google, Amazon, Microsoft and Facebook. So make sure you watch till the end. So before we begin, don't forget to subscribe to the channel and press the bell icon so you don't miss on daily problem solving videos. So let's get started. So the problem statement says, given a binary tree, find the lowest common ancestor LCA of two given nodes in the tree. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in the tree that has both P and Q as descendants, where we allow a node to be a descendant of itself. So we have given a binary tree and nodes P and Q, we have to find the lowest common ancestor. Here ancestors are nothing but the parent node of a given node, that is 3 is the ancestor of 1, 3 is the ancestor of 5. Whereas 5 and 3 are the ancestors of 2 and 3 and 1 are the ancestors of 0 and 8. So we have given two nodes P and Q and we need to find the lowest common ancestors of both nodes P and Q. So let's understand this given problem statement with these two examples. So in example 1, we have given nodes 5 and 1. So for the nodes 5 and 1, we need to find the lowest common ancestor. The ancestor should be common and we need to consider the lowest one. Main point here is a node itself can be a descendant of itself. That is, a node can be an ancestor of itself. So let's get started with our example 1. So for the node 5 and 1, the ancestors of 5 are 3 and the ancestor of 1 is also 3, and the common ancestor of both 5 and 1 is 3, and also it is the lowest one, so we'll consider 3 as a lowest common ancestor of both nodes 5 and 1. So our answer for our example 1 would be 3. Coming to the example 2, here we have given nodes 5 and 4 and we need to find the lowest common ancestor of both nodes 5 and 4. So let's go step by step. So the ancestor of 5 is 3, that is the parent node, and the ancestor of 4 are 2, 5 and 3. For the node 4, we have 3 ancestors, that is 3, 5 and 2. So the lowest common ancestor of both the nodes 5 and 4 would be 5, because as per the definition of LCA, a node can be a descendant of itself, that is a node can be an ancestor of itself. So for the node 4, 5 is considered as a lowest common ancestor. For the node 5, 5 itself can be an ancestor. So therefore, the LCA of both nodes 5 and 4, since the node can be a descendant of itself according to the definition of LCA, the output of this given example would be 5. Coming to the example 3, we have two nodes, that is 1 and 2, and we need to find the LCA of both this node 1 and 2. The ancestor of 1 is nothing, that is we don't have any ancestor of 1 as it is a root of the tree, whereas the ancestor of 2 is 1. So according to the definition of LCA, a node can be a descendant of itself. So the lowest common ancestor of both nodes 1 and 2 is 1. So this was all about the problem statement, lowest common ancestor of a binary tree. So let's get started with our brute force approach. So let's again understand the concept of descendants with this given example, that is given node P is equals to 5 and Q is equals to 1. So since node 5 is in the left subtree of 3 and node 1 is the right subtree of 1, so the lowest node that has node 5 and node 1 as descendants. So here the lowest node that has both 5 and 1 as its descendants is 3 itself. So that's why for this given example we'll return 3 as an output. So let's get started with our brute force idea. So here the idea would be to store the path from root to P and root to Q. And then we'll compare both the paths to find the last common node. So here for the node P, that is 5, we'll store the path and the nodes from root to this given node P, that is 5. So for the node 5, the path contains node values from root to 5 would be 3 and 5. And for the node Q, the path contains node values from root to the node 1 is 3 and 1. So after extracting both the paths for the node P and Q, that is from the root to the current node P and the root to the current node Q, we'll compare both the path and we'll find the last common node, which would be our LCA of both the nodes P and Q. So let's quickly compare it. So we'll compare first element of both the paths, that is 3. So they both are common. So this could be our possible answer. And when we move to the next element, that is 5 and 1, so they are not equal, so we'll again move to the next node. Since that is the end of both the paths of P and Q, so our last common node of both the paths is 3. So the lowest common ancestor of both the nodes P and Q is 3. So let's consider other nodes, that is P is 5 and Q is 0. So let's again extract the path from root to P and from root to Q. So the path for P would be 3 and 5, and the path from root to Q, that is 0, would be 3, 1 and 0. So after getting the path of both the nodes P and Q, we'll again compare both the paths and we'll find the last common node. So here, since we have found the first common node, this could be our possible answer. Then we'll move to the next values, that is 5 and 1. So since they are not common, so we'll again move to the next node. So since we have ran out of values for the path P, we'll return our last common node which is stored in our LCA variable. So for this example, P is equals to 5 and Q is equals to 0, our LCA would be 3. So let's take another example, P is equals to 5 and Q is equals to 4. So our first step here would be to extract the path from root to this given node P and root to this given node Q. For the node 5, the path contains values 3 and 5, and for the node 4, the path contains values 3, 5, 2 and 4. After getting both the path values from both the nodes P and Q, we'll compare the values and we'll find the last common node. So let's start comparing. So the first two values are same. So let's store this value in LCA variable, that is 3, and move on to the next node. So the next values are 5 and 5. So again they both are common. So we'll update our LCA variable from 3 to 5. And since the path values of node P has finished, we'll stop our iteration and we'll return the value which is stored in the LCA variable, that is 5. So for this example, where P is equals to 5 and Q is equals to 4, the lowest common ancestor value is 5. Now let's try to understand the time complexity and space complexity of this brute force approach. So we are trying to find the path from root to node P and root to node Q. So finding path from root to node P takes O of n time, and whereas finding path from root to node Q also takes O of n time. So overall time complexity of this approach would be O of n. Whereas coming to the space complexity, the space complexity would be O of h, that is per path, which is maximum depth of recursion, plus O of h per storing each path. So total O of h to O of n. That is also depends upon the tree shape. So if the tree is a skew tree, then the space complexity would be O of n. But if not, then storing the path from root to that particular node Q would represent the O of height. So that would be the time and space complexity of this brute force approach. So let's quickly code this approach and let's submit. So here's the code for our brute force approach. So since our brute force approach stores the values present in that particular path, so here I have taken vector of type tree node, which would store the values present in the path from root to P and from path root to Q. So I have named both the vectors path 1 and path 2. I have called function getPath by sending root value P node and path 1 vector, whereas root value Q node and path 2 vector. So this particular function will extract all the values present in this path from root to P and the values present in the path from root to Q. So let's check this getPath function. So it would take parameters root, target and path vector. The base case here would be if root is null, we'll return false. We'll first push back the root value and we'll also check if we have reached the target value or not. So if the root value is our target value, we'll return true, and we'll call the function if getPath by sending root left and target and path, also root right, target and path. So here we are trying to search for the target in this given tree, and while searching the target we are trying to push all the values inside our path vector. And for a recursive path, if we didn't find the target, we'll remove all the values from the path vector as we haven't found the target in that particular route. For example, if our target is node 2 and if you are starting from a root node 3, if you are sending the root left call from this particular point, and since we are calling getPath and sending root left, the call gives to 5 and again 5 gives calls to 6, and while giving these calls we'll store these values in our path vector. and after reaching 6, and then we have found a null value, and since we haven't found the target value, that is 2, we are returning back to the previous call, and while returning we'll remove this particular 6 value from path vector. So in this way, after finishing these calls, and if we haven't found target node, we'll try to remove the values which we have pushed in our path vector using path.popback. So in this way, with the help of backtracking and with the help of recursion, we'll try to find a target node, and if we found the target node, we'll return true, and all the values which are present from root to that particular target node will store in our path vector. So in this way, with the help of our getPath function, we'll store all the values in our respective path vectors, and after all the values we have extracted from this function and stored in path vectors, we'll take a variable LCA which would be initially null. We'll also take the pointer I which would be initially 0, and we'll use a while loop to compare both the values in these both vectors, path1 and path2. So the condition would be, since I less than path1 dot size and path2 dot size, and path1 of I should be path2 of I, which means both the values in both the vectors should be common. And if it is, then we'll update our LCA variable with that particular value and we'll move our I pointer. And if we have reached a point where there is no common node, we'll stop this iteration and we'll return our LCA variable, which would be the last common node, and which would be our resultant answer, that is lowest common ancestor. So this is how our brute force approach works. The time complexity of this approach would be O of n, and the space complexity here would be O of n as well, as we are storing the values from root to that particular node with the help of these two vectors. So let's quickly run this code. It's working, so let's submit. As you can see, this approach gives us successful submission. It is less efficient when we try to work on larger trees where the number of nodes is very high, and since we are also using an extra data structure to store all the values, that is the path values present from root to node P and root to node Q. So let's try to optimize this approach, and let's not use any external data structure like vector to store the values, and complete this problem statement in a single recursive call. So let's optimize our approach. So in our optimal approach, we'll use post order traversal. So post order traversal works like this. So sends the recursive call to its left subtree and right subtree, then it reaches to root. That is, first it moves to left node and then right node and then the root node. So the optimal approach works like this. So if the current node is null, then we'll return null, and we'll send left recursive call and right recursive call for each node. And if both sides return non-null value, that is, we have found P or Q value from both sides of the recursive call, then we can say that the current node is a LCA. If current node is P or Q, we'll return current node. So these two cases would be our base case, and we'll send the two recursive call by sending node left and node right, searching either P value or Q value. So if both of the recursive call gives us a non-null value, that means we have found our P value or Q value in each of our recursive call, then we can say that the current node is a LCA. If not, then we'll return the non-null side. That is, if we have found in left subtree, then we'll return the left subtree value, and if we have found the value in the right subtree, then we'll return the right subtree value. So this would be our optimal approach. So let's quickly dry run on this given example and see how our optimal approach works. So we'll start DFS from root 3 here. So it will send the DFS call to its left, as the post order traversal starts from the left subtree. So 3 gives a call to 5, and it will check if the current node is null or not. So it is not null, and if it will also check if the current node is either of the value P or Q. So since here P is 5 and Q is 4, so since here the current node is equals to P, we'll return 5 from this left call. So LCA of 3, that is the DFS call which we have given from the root 3, the left subtree value gives the value 5, and then we'll start giving a call to the right subtree. So 3 gives a call to right subtree. So it will check if the current node is null or not. So it is not null. So here it will also check if the current node is equals to either P or Q. So since we have already found P, now we'll check whether it is equal to 4 or not. So since it is not 4, so based on the post order traversal, it will again go to the left subtree So it will check with 0. Now it will move from 0 to 8. It will check if the current node is equals to q or not. So since it is not 4, it will again go back to the root value. And 1 gives null to a main call. So we haven't found the q value in our right subtree, which means for this given call we have found the value from its left subtree itself. So the LCA of this given binary tree for p is equals to 5 and q is equals to 4 is 5. So let's take another example, that is p is equals to 5 and q is equals to 1. So again it will start DFS call from 3. First it will give a call to its left subtree. So here again, since the current node is equals to p, it will return 5 as a result of a left call to the root. And again 3 gives a right call to its right subtree. And here since the current node is equals to q, it again gives 1 as a result for its right call. So now the current node has both non-null values from its left call and right call, which means the current node can be considered as the lowest common ancestor of these two values. Hence, for this given example, that is p is equals to 5 and q is equals to 4, the LCA would be the root value, that is 3. Let's take another example, that is p is equals to 6 and q is equals to 0. So again we'll start DFS call from 3. It will give left call to its left subtree and right call to its right subtree. So left call will check whether the current node is equals to p or not. So since it is not equal, like it again gives a left call to its left node value. So here since the current node is equals to the p, will return p to its root node, and again this 5 will give 6 as a answer for its left call. So the 3 gets answer 6 from its left call. Now according to the post order traversal, we will move to the right subtree. So 3 gives a right call to the right node. We'll check if the current node is null or it's equal to either of one of the value p or q. So since these both conditions fail, we'll again move to the left node. So now here the current node is equals to the q value. So we'll return 0 to its root value 1. The 1 returns 0 to the call sent by the 3 node. So now the current node 3 got 2 null values from its both call, that is left call and right call. So which means the current node can be considered as the lowest common ancestor for both p value and q value, that is 6 and 0. So for this example where p is equals to 6 and q is equals to 0, the LCA would be again 3. So the time complexity of our optimal approach would be O of n, that is we visit each node once, whereas the space complexity remains O of height, that is for the recursive stack where h is the height of a tree. So let's quickly code this optimal approach and let's submit. So here's the code for the optimal approach. So here the base conditions would be if root is null or root value is equal to the p value or root value is equals to q value, then we'll return root. We'll give 2 recursive calls, that is left and right, as post order DFS traversal starts from left and right and then root. So after giving these 2 calls, we'll check whether we have found the p value in left subtree or right subtree. For a current node, if we have found both p and q values from its both left call and right call, that is if left is not equals to null and right is not equals to null, then we'll return root, where root can be the possible lowest common ancestor. If not, we'll either send the left call value if left call has returned a non-null value, or we'll return the right call value. That is if left call is non-null value, then we'll return left, or else we'll return right. So let's quickly run this code. It's working, so let's submit. As you can see, this approach also gives us successful submission. Let's move to time and space complexity analysis. So in our brute force approach, the time complexity was O of n, where n is the number of nodes in the tree, whereas the space complexity was O of height per path, that is maximum depth of recursion, plus O of h for storing each path. So total O of h to O of n depending upon the tree shape. Whereas in optimal approach, the time complexity is O of n, that is we are visiting each and every node exactly once. And coming to the space complexity, it is O of height, where h is the height of the tree due to recursion stack. So here in optimal approach, the best case would be O of log n, and the worst case would be O of n. That is, O of log n is for balanced tree, and whereas O of n is for skewed tree. So this is the best case and this is the worst case. So that's it for today. Make sure to like the video, subscribe to the channel and leave a comment. And thanks for watching, and I'll see you in the next one.